So here we have 2.7 derivatives and rates of change. And this is the first time we see the word derivative. But basically, it has to do with, you could say, they're relating it to the tangent line of a curve and finding the velocity of an object. Those are two situations where we first encounter the derivative. It's a special type of limit. So tangent line to the curve. So if a curve has this equation, we have 2 points on a curve, one at x and one at a. Here's the slope formula, y minus y over x minus x. And let me just show you the picture. Okay, it's right here. We have 2 points on the curve, and there's a line between them. And that line is called a secant line. And really, that line is, you could say, extending out. So what they're doing is they're showing you the progression when this x, here's a, x starts out over here, the secant line is kind of flat, and then as x kind of goes towards a, moves towards a, these points start moving towards P, and the secant line, the line between them, starts changing and starts approaching this red line. And the red line is called a tangent line. And the tangent line only intersects the curve at this point, P. So the secant line intersects the curve twice, but ultimately when those points become a single point, that you'll just have a single point where the line intersects the curve. And at that time, you have that red line has a slope, and the slope of the red line is this equation here. So this is the limit as x approaches a dot. Now notice, when x gets to a, there is no x minus a, it's 0. That's the whole thing. And that's why we talked about last week, we said it's okay if a function has a hole in the graph, like when you get to that number where x is supposed to equal a, it's okay if x doesn't equal a at all. If there's nothing there, it could still be a limit there. And this is why, because we're going to have a 0 in the denominator. There's not going to be anything there. It's just when x is close to a that you'd have a fraction like this. But it's okay, because there's still a limit there. So we say the tangent line has a slope. There's a slope of the curve at a single point. We've never talked like that before. Okay, before this course, when you talk about a slope of a line, you're talking about a straight line on a graph. The whole line has a slope, has a single slope. It's the same slope at every point. Now, you have the curve, and when we say the curve, we mean the curvy curve, okay, this black line here. Okay, this curve has a different slope at every point, basically. The slope is always changing. And that's the difference between calculus and every other course before calculus, is you don't have a slope that's changing until now. So and then what they're saying here is the reason you could talk about the slope of a curve at a point is like if you zoom in to a curve, no matter how curvy it is, initially, if you take a small enough window, that curve kind of looks like a straight line, doesn't it? It kind of straightens out. And that's kind of the idea that in a short enough interval, a line is fundamentally straight. And we're gonna get back to that in like chapter 4 as well, where we talk about differentials. And when we talk about predicting another value on a curve by treating the curve as a straight line, basically. So that's also something else that happens. Now, this is another way to define it, okay? Instead of x and a, we have 2 points, a, but instead of the x being the other point, a plus h is the other point. And so in other words, we define the little distance between the 2 points as h, okay? And then we let h go to 0, okay? Just in this next slide, we take the limit as h approaches 0, okay? And so, of course, when you get to 0, you can't divide by 0, so there's nothing there when h gets to 0, but it's okay. And what they're saying here is you can apply this to a real-life situation where in the vertical axis you have distance. You're measuring distance away from something. So your distance is changing, like a car is going down the road, basically, and you're measuring it from a certain point. The car is like going away from you, and so the distance of the car from you is changing. It's increasing. So the distance is increasing, but this is time, okay? And that's in calculus, 99% of the time that horizontal axis is time. And so you're measuring distance over time, which is called rate, and in this case, velocity. And that's a very common application of slope, is to measure velocity, distance over time. And okay, so now they name it, okay? They say, okay, well, we have this slope of a tangent line. We have this change in distance over time. We see these things happening all the time. Things are changing. It could be change in a lot of things, really, a change in a population, change in a cost. This happens so often that we give it a name called a derivative. And this is a derivative of a function at a number a. Okay, so we're talking about the derivative of a function at a certain point. That's what we do in this section, 2.7. In the next section, 2.8, we're going to talk about the derivative as a function. Like we're going to keep this x, not a single point a. That's the difference between this section and the next one. Anyways, there's two formulas here, and we're going to use them both, like on our homework, on our worksheet. And they just mean the same thing. Two different notations that mean the same thing. So one's not better than the other, but I want you to be able to do both. And it's basically a lot of algebra that we end up doing. For example, I'm just going to slide this thing here through pretty quick, but we've seen this already, like where we put a plus h into the function, into this squared function. So, of course, the a plus h gets squared. You get a trinomial square. You get a lot of things. You expand it, and what I want you to notice here is that a lot of things cancel out. A squareds cancel out. The 9 cancel out. The 8a cancel out. Basically, everything without an h cancels out. And so what you have left is just the terms with h on the top over h, and then you get to factor out the h. They don't show this, but you factor out the h, and you cross out the h with the h below, and that's what's left, right? And that's what you do in pre-calculus. But in pre-calculus, you stop here. Okay, and you're like, I'm done. And then in calculus, you get to do one more step, and that's to take the limit as h goes to 0, and you get to put a 0 in for h, and it disappears. And then that's the derivative at that point a. A is a specific value of x. And then, of course, you could, at that point, put in a value for x and find the derivative or the slope of the curve at that point. Okay. And then we're also going to find, you'll see this on the worksheet, we're going to find not just the slope of a point, but we're going to find the equation of the tangent line itself, the line that goes through that point and has that slope. Okay, so this part of it, f of a, we're going to get from doing that whole big difference quotient that you just saw. And then we're going to just put in the point, we're going to be given this point, a f of a, so we'll just put that in and use point slope form. And rates of change, basically what we're talking about is, I just want you to be familiar with this notation. What are those triangles? How do we say that? Delta, thank you. Yeah, delta y. Delta means change. It's a Greek letter for D. It means change in y over change in x. So we're talking about this little line here over this little line. And that's how we calculate slope. Slope is the ratio of those two changes. But we're going to talk about when delta x goes to 0, what's going to be the slope at that point, x1, okay? And I just want you to, what they're pointing out here is, like, you see two tangent lines here. You see a tangent line at P and a tangent line at Q, and all they're pointing out is here, is the slope is very large at P. Do we agree? And then it's not as large, it's smaller, still positive, right? But it's smaller at Q. So what they're saying is the Y values are changing, okay? They're changing quickly at P. They're changing, but not as quickly at Q. And so, so the derivative could be small or large. It could be negative. And here, they're making a distinction, and we'll see this later, but they're making a distinction between velocity and speed. And what they're saying is velocity, it measures like how quickly you're moving, but you could be moving backwards and the velocity would be negative. But the speed, they're saying, is always positive. Okay, the speed is the absolute value of the velocity. So if you're moving backwards at a high rate of speed, you have a high speed, your speed is positive. So the speed is non-directional, but the velocity is directional. So just something to keep in mind. And this, just a little application, it says the cost of producing X yards of fabric is C. That's the function value. What's the meaning of the derivative? And I'll just tell you, the derivative is how fast, or the cost is changing, basically, or what is the cost per unit at that time? And so what does it mean to say the derivative at 1,000 is 9? And the answer is, when you produce that fabric, as you produce that 1,000th yard of fabric, it's costing you $9 per yard. Okay, that's your at that point in time. That's how much it's costing you per yard. And then it says, what's greater, the cost when you produce that 50th yard of fabric or 500th yard of fabric? And probably it's going to be cheaper just because of what they call economies of scale to produce. You're going to have that cost per yard cheaper as you produce that 500th yard of fabric, because you have some fixed costs, right? Costs for renting the space, turning on the machines, all those things that are not going to be different no matter how many yards you produce. And so it's not just about the fabric itself. Now, I said, when you get to 5,000, I don't know, maybe you're having to pay people overtime at that point, and your costs may not be as good. They may cost you. It may not necessarily be cheaper. Okay, so that's all I'm saying here.